Hi everyone, did you know the Earth is formed 4.6 billion years ago? Through these years, the nature has shown amazing time-tested structure and strategies which we can mimic and apply the concepts for sustainable architecture. And yes, I'm talking about biomimicry. Today, we are going to have a look on the Goal 11 of Sustainable Development, which is Sustainable Cities and Communities. Living in a city is very convenient as one can access to better education, job opportunities, healthcare and other facilities easily. But it is a challenge to maintain urban sustainability. While biomimetic architecture could be the solution. Let us look at some examples of biomimicry designs in architecture.
Our first example is algae wall.
What is algae wall? An algae wall is typically constructed by growing algae in a series of panels installed on the inside or exterior of a building. How the algae wall works? The sun which provides energy so that the algae can carry out photosynthesis and produce biomass. Biomass are fed into a biomass reactor in order to produce biogas. Biogas is then burned in the fuel cell in order to produce electrical energy which provides electricity to the house. When something burns, heat is released, which feeds into the power station of the algae house. Carbon dioxide is released and it is used to feed the algae in the glass panels. The power station saves and distributes heat for heating water of the house, and if there is surplus energy, it will be fed into community heating. And let's think about something important together. Can the algae wall be used in Malaysia? Well, here are a few reasons why it is a good fit. Malaysia is a great place for an algae wall because it has a tropical climate with lots of humidity and sunlight. These conditions are perfect for algae to grow and thrive. Therefore, the algae wall is a great choice for Malaysia because it can take advantage for the country's climate to grow and function well. What is the benefits of the algae wall? Malaysia has set ambitious targets to reduce carbon emissions and promote sustainable development. The cool thing is that the algae wall can help with that too. This is because during photosynthesis, the algae absorb carbon dioxide and release oxygen. This process can also help to insulate buildings and purify the air inside. Furthermore, algae-based biofuel is renewable and sustainable, and so it can be used to power buildings. As a result, it can help to reduce dependence on non-renewable energy sources. Algae can be used to power building heating, ventilation, and air conditioning systems, as well as lighting and other electrical systems. By using algae-based biofuel, buildings can reduce their carbon footprint and promote a more sustainable future. In conclusion, the algae wall is a perfect example of biomimicry in action. By emulating the natural growth and photosynthesis processes of algae, we can create sustainable building solutions that reduce carbon emissions and promote renewable energy. This innovative approach is both efficient and beneficial for both people and the planet.
Our second example is a termite mound-inspired ventilation system.
A termite nest can house up to 2 million termites, so the amount of oxygen consumed is significant. To prevent suffocation within the nest, a good ventilation system is required. The first way to create airflow in the space is to create a pressure difference, which is the venturi flow between 2 points by utilizing wind speed at different height. The lower wind velocity near the vertical chimneys at the ground level will result in high pressure that draw fresh air in and replace the warm air. The warm air in the mound will rise out into the central duct due to lower density. Then, it will experience the suction force exerted by the wind, moving towards the central chimney and out of the mound. On the other hand, the porous termite wall also plays a significant role in drawing in the fresh air. The Eastgate Center and Zimbabwe that apply this ventilation system consists of two buildings that are separated by an open space. The central chimneys at the top of each of the buildings are connected to a vertical duct where the warm air from the spaces within the building will pass through. Warm air will rise out from these spaces via the exhaust port at each floor into the central duct due to lower density. As the chimneys are exposed to higher wind velocity, lower pressure is created and hence the warm air flow out from the building. Meanwhile, the cold air from the shaded open space between the two buildings is drawn in by the fan installed at the first floor and enter the spaces in the building to replace the warm air. Besides that, the windows on the buildings also function like the pores within the termite wall to draw fresh air in. By using this biomimicry, the Eastgate Center consumes less than 10% of the energy of a building its size. Thus, it allows the Eastgate Center's owner to save 3.5 million due to the absence of an air conditioning system. Besides, it is also eco-efficient and is better for the environment as it causes less pollution.
Our third example is bacteria-based self-healing concrete.
Concrete, the most important construction materials that is widely used on Earth after water. However, concrete is prone to crackings, and its production contributes to over 8% of global carbon dioxide emissions. Thus, self-healing concrete can be an alternative to producing new concrete and reducing infrastructure's repair costs.
So, how can concretes autogenously heal their microcracks? Well, bacteria act as a healing agent, and the mechanism is called MICP, microbiologically induced calcium carbonate precipitation. When water enters through the microcracks, microcapsules dissolve and bacteria in it will be activated. They precipitate calcite crystals which can plug the cracks. This works effectively for cracks 0.8 mm or thinner. Then the bacteria sporulate and the whole process can happen again. So here are some examples of bacteria that can grow perfectly in alkaline condition and can germinate spores.
Bacterial-based self-healing concrete was successfully tested in the Netherlands and China on different infrastructure types such as wastewater purification tank, water reservoirs, metro station, showing the potentials to reduce harmful traditional repair methods and promote sustainability.
Now, let us see some advantages of self-healing concrete. First, it is cost-effective. We can reduce the cost of maintenance to repair the crack and damage of concrete since the concrete can repair the pores and crack by itself. Besides that, it is durable and safe to use. The additions of bacteria enhance the strength and durability of concrete by repairing the pores and crack which maintain the structural integrity of the concrete. This can prevent structural failure that compromise the safety of the building. Lastly, it is sustainable and has a long lifespan. Through this, it can help to reduce the environmental impact by minimizing the waste that is used in the constructions of buildings.
Here is our reference list. Please scan the QR code. Thank you!